Alright, this is a fairly complicated demo, so let's see if we can do it in a way that makes sense. So here's the little CNC mill that I'm working on. Right now I'm doing the optical Z-axis. So what we have is just a regular brushed DC motor up here, connected via a power driver thing to an Arduino. There it is. Which is basically just running a little bit of code that pulses the motor up and down. It doesn't do any fancy things with encoders or feedback. It just pulses it for, right now it's doing like a millisecond repeatedly, and then a delay in there, and then we can get some pleasant back and forth motion like this. The Z-axis can go up and down. It's going quite slowly at the moment. If you focus here. Quite slowly, just as a test, and because it makes prettier diagrams later on, which we'll see in a second. So instead of using a rotary encoder like I have on these other two axes here, that little thing on the shaft there is an encoder, or a linear encoder, which are fairly expensive for good ones. You can hack calipers, but they're slow. They only give you like 3 updates a second or so. What I decided to do was take a webcam. This is just the guts from a cheap, I don't know, $5 or $10 webcam off Amazon. It's a USB camera, so this is aimed at this little makeshift marking thing on the side of the mill. This is what the camera is seeing. So when this moves, you can see that the video updates accordingly. And the trick here is to get usefully calibrated data off of this movement. So what we have over here on this side is, this is just the raw camera image converted to grayscale. This is that same image averaged over columns, and then a hand window is applied basically to cut off the intensity on either edge. This helps with the Fourier transform goodness. And so what's happening here is that this is actually a 1D representation. It's just stretched out for easier visualization because it's hard to see a 1 pixel high thing. So what's happening is that this is being Fourier transformed. That data is stored for the past 500 frames that the camera is grabbing. And then for each frame that we get, we're doing a phase correlation between the most recent frame and all 500 of the past frames. There's a running bar along here somewhere you can't see. And wherever that bar is, which will become clear in a second. I guess I could have done this as like a moving waterfall type histogram, but this is a friggin' test bed app. Anyway, so the past 500 frames are being phase correlated, and there's a nice bright line at the first pixel. Is there anywhere where you can actually see this? No. Is that actually the pixel? It might be. It actually might be 2 pixels. So that means basically that there's no motion going on here. So when I actually move the axis, and it helps if I'm in the right window to do that. Alright, what's happening is that this is the most current frame, and these are the past frames. As you can see, there's no difference, that's this white line all across this edge, between the current frame and the past several frames, because nothing's moving right now. But when something does move, hang on a second. When something does move, then there's a difference in the phase correlation between these frames, and this exact offset is directly correlated to the amount of movement. And so by grabbing that data and comparing it sort of intelligently to the past frames, we can get a pretty accurate count of just how far this device has moved. Yeah, that's basically what this does right now. As well note, there's a little bit of lag when changing directions. That's actually the backlash in the nuts. Also interesting to note is that you can only get good data from relatively small movements. Obviously, if you shift everything on the frame off the frame and then compare those two frames, there's nothing to correlate, so there is no correlation. So there might be some drift over a longer period of movement, but that's another problem to figure out when it comes to it. All right.